Thank you very much to the organizers for setting up what looks like it's going to be a really fascinating conference, and for giving me the opportunity to review for you guys a little bit about what's been going on with the Sachdev-Yeh-Kitaev model. So the one-sentence summary of this system is that it's a strongly interacting quantum mechanics problem that is nevertheless solvable at large N. And in quantum mechanics, strongly interacting chaotic systems that are solvable are few and far between. So this, I think, should be understood as a rare resource. And different people from different areas of physics will have different ideas of what to do with this. I'm going to touch on some, but not all of these ideas. And of course, there are many others that I won't be able to discuss. But, okay, so the basic plan of the talk is here. I should warn you that by the standards of review talks, it might be a tiny bit technical. There's two reasons for that. One is that the techniques involved in analyzing the model are really interesting, but also just because, since this is the first talk of the conference, you guys are all razor sharp, and I'm sure you'll have no trouble keeping up. Okay, so let's get straight into it. What is the SYK model? So this is a quantum mechanics of n interacting Majorana fermions. In 0+1 dimensions, what n Majorana fermions means is just a collection of n matrices that satisfy this anti-commutation algebra. So there are ways of constructing these guys out of tensor products of Pauli matrices. This is nothing but the algebra satisfied by Dirac gamma matrices in n dimensions. It might be useful to keep in mind the currency conversion, which says that if you want to build a Hilbert space for n Majorana fermions, you need to use n over 2 qubits. So anyhow, these are a concrete collection of matrices, 2 to the n over 2 by 2 to the n over 2 dimensional matrices. And we should go about trying to find a Hamiltonian for a system that describes them. So a general Hamiltonian, which should be a bosonic operator, could be written as an expansion with a quadratic term, a 4 Fermi term, and so on. The SYK model is a special case of this, where we have only 4 fermion interactions, but we allow sort of the most general thing. So we add all possible 4 fermion interactions to the Hamiltonian with random coefficients. So the idea is that the SYK Hamiltonian isn't really a particular Hamiltonian, it's an ensemble of different Hamiltonians. The ensemble is defined by the collection of these couplings, J, with 4 indices. And specifically what we do is we imagine that J is drawn from a Gaussian distribution with mean 0 and with variance given by this expression here. So the symbol capital J sets the scale of the Hamiltonian. It has dimensions of energy. And this factor of n cubed is here to make sure that we have a nice large n limit. Okay. So a couple of comments about this system. First, we can make a dimensionless coupling by taking this scale of the Hamiltonian J and multiplying it by the inverse temperature beta, which is 1 over T. That's a dimensionless combination, and the interesting physics in the SYK model is in the strongly coupled or low temperature region, where beta times J is much bigger than 1. Sometimes it's useful to think about a small generalization of SYK, where instead of having 4 fermions interacting, you have an interaction term that has q fermions. So q could be 4, 6, 8, sometimes also 2, although that's an exceptional and kind of stupid case where you just have a random mass matrix. And then finally, a slightly technical point is that this system self-averages very well at large n. What that means is that a given realization of the couplings gives for you a fixed Hamiltonian that has properties that are very similar to the ensemble average. This allows us to get by without thinking about replicas or replica symmetry breaking. It makes life considerably easier. Okay, so that's what the model is. One of the nice things about it is that it feels as though almost any technique from physics can be applied to it, and it just sort of works really well. So one example of a really crude technique from physics is you can just think about the Hamiltonian. Well, all right, that's a matrix. We can diagonalize it and plot a histogram of the energy eigenvalues. So here's what you get when, let's say, we have 34 fermions. For for two cases. So this is the sort of stupid case Q equals 2, which corresponds to a random mass matrix. And this is the more interesting SYK case with Q equals 4. And this is a histogram of the energy levels of this Hamiltonian. There's just two things that I want to point out. The two things contrasting these two pictures. So the first is that it might be hard to see, but the curve here in the Q equals 4 case is much smoother than in Q equals 2. That turns out to be a consequence of level repulsion between the eigenvalues, which is a symptom of chaos in this Q equals 4 model. The detailed statistics of eigenvalues are actually quite interesting, and I think Schenker is going to discuss that some more in his talk later today. The other thing has to do with the behavior of the density of states near the ground state. So in the Q equals 2 model, we have these tails at low energies, so that by the time we get to the ground state, the density of eigenvalues is quite small. Whereas in the Q equals 4 model, the spectrum ends rather abruptly, so near the ground state, the density of eigenvalues is still fairly high. This is something that we're going to come back to a couple of times during the talk. It's related to something called the zero temperature entropy of this model. Okay, so a slightly better technique in physics that also works well for this model is resummed Feynman diagram perturbation theory. So here's a, let's imagine that we think about the 2-point function of fermions, so G is the 2-point function of fermions. Here's a typical Feynman diagram that contributes to that at large n. So this is a diagram that survives in the large n limit. And well, it looks fairly complicated, but actually it's generated in a simple way by starting out with this propagator here, and then iteratively decorating whatever propagators you see with these circular self-energy insertions. Not only is it simple to characterize, these diagrams are simple to sum by writing down equations for the self-consistency equations for the sum of all diagrams. So these are those equations. G is the 2-point function here in frequency space. What this first equation says is that G is a geometric series of self-energy diagrams, 1pi self-energy diagram, where we have these blobs here, but we can have any number of them along the propagator. And then the second equation says that those blobs are themselves built out of products of the fully dressed 2-point function. So this here you can think of as sort of, again, a version of this whole diagram. So these are the equations that you get that determine the full sum of all of these diagrams. These are sometimes called iterated watermelon or melonic Feynman diagrams, because it's supposed to look, well, something like melons. Okay, so one approach to these equations is you can solve them on a computer just by iterating them. But you can also solve them analytically in some limits. So for example, if we think about the model at very weak coupling, then we might be able to ignore this term in the denominator and get basically the free propagator back. More interestingly, in the strongly coupled limit, which is like the IR limit, it turns out to be allowable to drop the first term in the denominator here. And then we get a somewhat simpler set of equations. And these have some nice exact analytic solutions. So if we're working on the line, this would be like zero temperature. Then there's this power law solution for the 2-point function. And if we work on the circle, so the circle here is the circle of imaginary time, the finite temperature circle of imaginary time, where time runs from tau equals 0 to tau equals beta, the inverse temperature. If we solve these equations on the circle, then one finds, well, it looks slightly more complicated, but still a very simple solution, like 1 over a power of sine tau. Now, the thing to note about these solutions is that they are exactly what you would expect for the 2-point function in an SL2R invariant theory in one dimension. So the SL2R acts in this case in the usual fractional linear way. On the circle, it acts in this way. It acts as fractional linear transformations of this variable, this tangent of tau variable. Okay. Well, you might be justified in being a little bit skeptical that you actually get these solutions starting from these equations and dropping this term. So here's some numerical plots of exact solutions of the 2-point function for 3 different values of the coupling. There's fairly weak coupling, intermediate coupling, and stronger coupling. These diagrams here are supposed to represent the separation of the fermions on the circle, just labeling what the x-axis is. So this is G as a function of tau. And I've also drawn a couple of other things on the plot. So this dashed green line is the 1 over sine tau to a power computation. And you can see that already at this value of the coupling, beta j equals 50, the agreement is reasonably good. It gets better at stronger values of the coupling. I also plotted this dotted red line here, which is the exact 2-point function computed by diagonalizing the matrix when you have n equals 24. So you can see that the 1 over n effects are reasonably controlled already in this case. I should have mentioned on the previous slide that, well, these equations have the form of an SL2R invariant 2-point function, and they identify the conformal dimension of the fermion in the SYK model as being 1 over q. So q, remember, was the number of terms appearing in the interaction. For most of this talk, you can just set q equals 4. So the conformal dimension of the fermion is a quarter. Okay. So a lot of the interesting physics in SYK has to do with real time. And so it's interesting to think about taking this 1 over sine tau answer and analytically continuing it with tau goes to it. Then you find a 2-point function that's decaying exponentially. The interpretation of this is that the single fermion operators are leaking into the space of more complicated products of many fermions. And that's why we get exponential decay in the 2-point function. This is actually the basic effect behind chaos in this model, which is something that we'll discuss a little bit more later in the talk. Okay, so far we've been talking about analyzing this model by thinking about Feynman diagrams, and there's just a fact that they form a set of diagrams that can be solved, that can be summed in an efficient way. But in the next part of the talk, we're going to try to understand some variables where it's obvious that the model is simple and solvable at large n. Those variables will have the advantage that they'll allow us to understand in a more systematic way the interesting low energy physics of SYK. So this part might be a little bit technical and maybe slightly unfamiliar, but please stay with me. Okay, so to start, let's write a formula for the path integral of this SYK model with fixed values of this disorder couplings J with 4 indices. So that looks like this. Now it turns out that the thing that's simple at large n in this model is not a particular realization of the partition function, it's the disorder average that has a simple expression. So we can think about doing the average over these couplings by integrating over this variable with a Gaussian weighting. We can do that inside the path integral over fermions, and then we get a rather complicated expression. When we Gaussian integrate over this term, we'll get an 8 fermion term at 2 different times. This doesn't look very promising. But the idea is that you can simplify that theory by introducing 2 new variables. These variables are called G and sigma for reasons that you'll appreciate in a few moments. Both of them are bilocal fields, so they depend on a pair of times. The purpose in life of sigma is to be a Lagrange multiplier that enforces a constraint that sets G equal to an average bilinear of the fermions. This equation is red because it's going to be important. The thing to remember is that, well, G is a bilinear in the fermions, so for example, a 1-point function of our new variable G would be a 2-point function of the fermions. Okay, the point of introducing these variables is that you can then integrate out the fermions. And then we get this theory here. The action in terms of G and sigma has these 3 terms. This one comes from integrating out the fermions. This one is a leftover from the Lagrange multiplier. And this is the fermion interaction in our new and sophisticated bilocal variables. This is a really unpleasant looking action. It's a function of bilocal fields, and it's non-local in time. The reason that we go through this procedure is for this factor here. The action is multiplied by a factor of n in the exponential, which means that at large n, this integral is easy to think about. The path integral over G and sigma is easy to think about. You should find the saddle point, and then you should look at small fluctuations about the saddle point. That's the reason why this model is solvable at large n, because it has this formulation. So, okay, so what are the saddle point equations? Well, we can vary with respect to G and sigma in this action, and we find these equations. If we make a further ansatz that G and sigma depend only on the difference of times, then we get exactly the equations that we found by looking at the self-consistency condition for those Feynman diagrams. So in particular, this gives us the same equation for the two-point function, because these saddle point equations will give us the one-point function of G, and the one-point function of G is the two-point function of the fermions. So we get back the same conclusion by studying the saddle point equations of this theory. We can do more, though. So one thing that we can do is we can take the solution and plug it back in to the action to get a large N approximation to the partition function. And you can do thermodynamics on that partition function to compute the entropy of the model. Here I'm plotting the entropy divided by N as a function of the temperature. So, okay, that's plotted here for 3 different values of Q. Let's focus for the moment on the Q equals 4 case. The thing I want to point out here is that as we take the temperature to 0, this entropy does not vanish. It approaches some constant, like 0.23 times N. This constant is referred to as the zero temperature entropy, and there's a lot of interesting physics behind this. Well, what does it mean? The density, what the entropy tells us is about the exponential of the entropy tells us about the density of states at an energy corresponding to the temperature that we're looking at. And at zero temperature, we should be looking near the ground state. And what this tells us is that there is actually an exponentially large density of states near the ground state. That's not true in the Q equals 2 model, where the entropy vanishes at zero temperature. And this is consistent with those plots that we saw earlier, that by the time you get to the ground state in Q equals 2, the density of energy eigenvalues is quite small. Okay, so, well, these are, well, maybe more important than the exact answer is the fact that the way that we compute the entropy in this model is rather similar to the way that you would use gravity to compute entropy in a more conventional holographic theory. So there you solve the saddle point equations, which are Einstein's equations, and you plug in your solution to compute the partition function. Here, the variables that are classical are G and sigma. So in some sense, we should think about G and sigma as being variables that are related to the bulk description of a more conventional holographic theory. Okay. So now, another thing that we can do with this G and sigma action is we can try to systematically understand the infrared behavior of the model. This is where the low temperature physics, where the SYK model is interesting. So to do this, what we can do is we can drop the time derivative term in the effective action. That's analogous to dropping the minus I omega term in the denominator that we used earlier to get simplified equations for the two-point function. But here we can do it at the level of the action. If we drop the d tau term, we get this marginally simpler looking action. And the important thing about this that was noticed by Kitaev is that this action is reparameterization invariant. So it's time reparameterization invariant. So tau here is the time variable that's running between 0 and beta on the circle. And we can define a reparameterization phi of tau to act on the fields G and sigma in this way. And then one finds this action is invariant. I mean, this term is, well, it's pretty clear. If we take q powers of this factor, this will turn the d taus into d phis, and we'll get the same expression. So what we conclude is that in this IR limit where we can drop the d tau term, this theory has a full reparameterization symmetry, or diff S1 symmetry. This is also what you would call the full conformal group in one dimension. So the model is developing an emergent conformal symmetry in the infrared. That actually is not quite right. The more correct statement would be that the model is trying to develop a full conformal symmetry in the infrared, because there's a problem with this. The problem is that our solution to the saddle point equations at finite temperature, which look like 1 over sine tau to a power, that thing only has SL2R invariance. It doesn't have the full diff S1 symmetry. So when we expand about this solution, well, we can think about the solution as spontaneously breaking the full symmetry of the problem, and then we expect to find a bunch of Nambu-Goldstone bosons. So those guys will live in the space, the full group modulo the preserved subgroup, which is diff S1 mod SL2R. And when we integrate over these zero modes, we'll get a divergence in the path integral, because we're integrating over bosonic coordinates with no action. Now this is a problem because our partition function, well, we're studying a simple problem with a finite number of fermions, and the partition function should be finite. So we've done something wrong. And the thing that we've done wrong is taken this IR limit too naively. So what we have to do is we have to back off the IR limit a little bit, and then one finds that these zero modes, these Nabu-Goldstone bosons, get lifted slightly. So here I've drawn a cartoon of the integration space over sigma and g, these bilocal fields. The saddle point of the theory is represented by this green dot here. And the statement is that at low temperatures, we have a locus emanating out of the saddle point, which corresponds to these Goldstone modes. And they have surprisingly small action, but it's not zero. So the correct statement is that the action for these modes is proportional to n, because every action in this theory is proportional to n because of that factor that we found earlier. But it's suppressed by a factor of this large coupling, beta j. So in the IR limit, the action along this direction is suppressed, and the action in other directions, which don't correspond to these Goldstone modes, is large. It's of order n. Okay, and again, the definition of these Goldstone modes is just that they're reparameterizations of G star, which is the saddle point, the green dot. So to understand this theory better in the low temperature limit, what we should try to do is understand the action along this red curve. And you can get the right answer by thinking about this from the perspective of effective field theory. There, what you would do is you would write down a local term with the lowest order in derivatives that's consistent with the symmetries that we have. The most important symmetry in this case is the fact that the Goldstone boson phi is living not in diff S1, but in diff S1 mod SL2R. This is always the way Goldstone bosons work. They live in the full group modulo the preserved subgroup. So SL2R acts on the reparameterization phi in this way. This is linear fractional transformations of tangent phi over 2. And the lowest order in derivatives local action you can write down with that symmetry is this action. So it's the integral of the Schwartzian derivative. This is sometimes called the Schwartzian action. I'll write a more explicit formula for this on the next slide. But let me just note a couple of things about the coefficient. So first, it's proportional to n for the same reason that the overall action was proportional to n. But we have a factor of 1 over j, which reflects the suppression of the action along these directions. You can also think about that 1 over j as being because the Schwartzian is a dimension 2 operator, so it's an irrelevant term. And so we need the factor of j for dimensional consistency. Okay, so this is the end of the sort of technical and somewhat unfamiliar part of the talk. I'm just going to give a mini summary. So what we did was we started with SYK in terms of these fermions with disorder. Then we introduced these new variables, G and sigma, to simplify and write the partition function in a way where it's completely obvious that the theory is simple at large n. Then we investigated the saddle point and the fluctuations about it. We found these interesting Goldstone modes, and then we identified the leading action for these modes. So here's a more concrete expression for this action, where you write out the Schwartzian explicitly. And it's important to note that this action, because of this factor of 1 over j here, because this is dimension 2, this action for the phi modes breaks this conformal symmetry, breaks the physical conformal symmetry of the model explicitly. So the model tries to have this conformal symmetry in infrared. If it had the symmetry, it would have unleashed these Goldstone bosons, which would lead to a divergence. The Goldstone bosons are controlled by this action here, but that action breaks the conformal symmetry. Okay. So now we can have a little bit of fun understanding some properties of this Schwartzian action and using it to relate the model to the physics of ADS2. So there was going to be 4 of these little mini sections. First, we should discuss what we would mean by a theory of gravity in 2 dimensions. Your first guess for a theory of gravity would be this thing here. This looks like the Einstein-Hilbert action in higher dimensions. But in 2 dimensions, this is too simple. The reason is that the expression in brackets here is a topological invariant that for the class of metrics we'll be studying is just 2 pi. So this whole action reduces to a constant, which is definitely too simple to be an interesting action for a two-dimensional theory of gravity. So you can motivate how to come up with a better guess for the action by thinking about cases in higher dimensions where you have an approximately ADS2 factor that appears in the metric. So the classic example of this would be a nearly extremal black hole in higher dimensions. And if you look there, then one finds an action that includes a term like this. This gives the extremal entropy of the near extremal black hole. And then there's a universal correction term, which we can write in this way. It involves a coupling between the metric and a scalar field f called the dilaton. In the higher dimensional cases, f is related to the size of the other directions in the space. Okay, and if you study this higher dimensional problem, you'll also find higher order terms, some massive fields from the KK reduction, but in the nearly extremal limit, this term is the most important. So we're going to focus on this term. This theory has a name. It's called the Jakiv-Teitelbaum theory of gravity, and it was reinvigorated a few years ago, pre-SYK, in a paper by Almiri and Polchinski. For our purposes, the important point is that this theory actually reduces exactly to the Schwartzian theory that we discussed before. So to show that, you proceed in 2 steps. Step 1 is to imagine integrating over the dilaton f. This inserts a delta function in the path integral that sets r plus 2 equal to 0. In 2 dimensions, constraining the scalar curvature is a big deal, and setting r plus 2 equals 0 tells us that we're looking at a piece of rigid hyperbolic space, rigid hyperbolic 2 space. But it doesn't tell us exactly which piece, so in the second step, when we integrate over the metric, what we end up doing is integrating over different shapes that we can cut out of the hyperbolic disk. So how can we parameterize those shapes? Well, here's an example of a cutout geometry from the hyperbolic disk. The most natural parameterization might be to give the hyperbolic radius rho as a function of the angle in polar coordinates. That one is okay, but more convenient for our purposes is to give a different parameterization, which is the angle phi as a function of the proper time or proper length along the boundary curve. So a boundary condition for our problem is that the total length of the boundary should be related to the inverse temperature. It should be beta divided by the holographic renormalization parameter epsilon. So we can parameterize the boundary here as by tau over epsilon. And then, okay, we can describe these cutout geometries by giving a function phi of tau. What is the action for phi of tau? Well, this term vanishes because r plus 2 is 0, so we focus on the boundary term, this extrinsic curvature, and it's not too hard to show using holographic renormalization that that reduces exactly to the Schwartzian action. So we started with in principle, 2-dimensional theory of gravity, this Jakiv-Teitelbaum model, and we found that in fact it reduces to a 1-dimensional theory. That 1-dimensional theory is exactly the Schwartzian theory that we got from SYK. Now, in Euclidean signature, this Jakiv-Teitelbaum model is a theory of cutouts from the hyperbolic disk. In Lorentzian signature, we can analytically continue, and we find a simple theory of a 2-dimensional black hole. There's going to be a lot more discussion of the Lorentzian version of this model in Maldasena's talk, which is up next. But we can say for the moment that the SYK model can be understood as a quantum mechanical completion of the Jakiv-Teitelbaum 2-dimensional black hole, in the sense that it's a well-defined quantum mechanics system that reduces at large n and low temperature to the JT gravity. Okay, so comment 2. One of the reasons why people say that the SYK model is very strongly interacting is that it saturates a general bound on chaos in quantum mechanics. quantum systems. So chaos in these types of systems can be diagnosed by looking at the square of the anti-commutator of simple fermion operators at different times. Now, under time evolution, Feynman diagrams like this one that we discussed earlier in the talk take a simple one fermion operator and turn them into a sum of products of many fermion operators. And what this quantity is measuring is roughly the probability that at time t, one of those daughter fermions will be of type B. If we start out with a fermion of type A, that one of the daughter fermions will be of type B. And that's expected to grow exponentially just because these Feynman diagrams grow exponentially. So this is the generic expectation in this type of system for the behavior of this anti-commutator squared. Now, the surprising thing about SYK that was pointed out by Kitaev is that this model saturates this chaos bound that states that the coefficient lambda L can never be bigger than 2 pi over beta, so 2 pi times the temperature. So in some sense, that means that the SYK model is as strongly chaotic as is allowed in any quantum mechanical system. Now, it looks complicated to analyze these types of diagrams, but using our fancy Schwartzian effective theory, it's actually very quick to get this result, this e to the 2 pi over beta times t behavior. So the way you do that is just by looking at classical solutions of the Schwartzian theory. So we can expand about the simplest saddle point where phi of tau is equal to tau. That's like an unreparametrized circle with a small wiggle epsilon of tau. And then if you look at the classical equations of motion, you find 4 solutions. It's a 4-derivative theory, one of which is growing exponentially in real time with precisely this maximal coefficient. And then I'm not going to go into details here, but roughly speaking, in this computation, one of the fermions sources this exponentially growing mode, and that leads to this exponential growth in this expression. Now, you might be worried that this growing mode indicates an instability of the Schwartzian theory because we have an exponentially growing classical solution. But in fact, for most purposes, this guy is pure gauge. So linearized SL2R transformations, when expressed in terms of epsilon, take this form, and we can choose one of these terms to cancel the exponentially growing term here. Remember that the SL2R, this is the SL2R that's acting on tangent of phi over 2, and it's a gauge symmetry because we're integrating over phi in diff S1 mod SL2R. Anyhow, so these exponentially growing modes are only physical in quantities sort of like this, where we compare what would have happened if we had versus hadn't acted with a perturbation. For those types of situations, there's no SL2R frame which removes the growing mode in both cases, so it physically contributes. This sounds like a little bit intricate and unfamiliar, but I think it's actually something that's more or less familiar from thinking about conventional classical chaotic systems. So let's imagine a bath of water or something like that, and here I'm plotting a couple of trajectories in phase space. The red trajectory differs from the black trajectory because we make a small perturbation at this point, and then it moves away exponentially. So in this type of system, the butterfly effect, which says that we get this exponential deviation here, is a kind of instability, but it doesn't mean that baths of water explode if you poke them. The reason is that the very different places that we end up look quite similar to each other. And in fact, the type of quantity that would be sensitive to this exponential would be a quantity where we compare what would have happened if we had versus hadn't made this perturbation, just like we were discussing on the previous slide. So in the SYK model, the fact that these places are similar and the exponentially growing modes don't appear in simple quantities is enforced in an aggressive way by this SL2R invariance. Okay, comment 3. So far we've been thinking about the model in an approximation where n is bigger than anything else. So in that case, even though the Schwartzian action has this coefficient n over beta j, n is still very big. And the coefficient is large enough to suppress fluctuations of this Goldstone boson field. But if we go to very low temperatures, then this coefficient n over beta j will become small. And if that happens, the coefficient of that action becomes small, and it allows large fluctuations in our degree of freedom phi of tau. So here are some Monte Carlo snapshots for different values of this coupling. So it looks, based on this, like the low temperature physics of SYK should be complicated, described by a strongly fluctuating theory. But something nice happens, and it turns out that the partition function is one loop exact. So you can write an exact expression for the partition function of the Schwartzian that includes all these fluctuations, where we have a power of beta j that comes from a one loop term, and then an exponential that comes from the saddle point. And that makes it possible to accurately describe the very low temperature behavior of the partition function. And from that, one can extract a density of states by trying to solve this equation. And it has a solution here. Now, one thing that's interesting about this formula is that at low energies near the ground state, it vanishes like a square root, which is familiar from the behavior of the energy eigenvalues of a completely random matrix. And it's interesting that we get that behavior, in this case, by summing over these large fluctuations of phi of tau. Another thing to note about this is that this is a continuous function of energy, which is a problem that we'll come back to maybe at the end of the talk. Okay. So then finally, we should also think about the other directions in functional integral space. So far we've been focusing on this one direction corresponding to these pseudo-Goldstone modes. But there are other directions, an infinite number of other directions. Those guys have action that's proportional to n, not n over beta j. So at low temperature, their fluctuations are much smaller than the fluctuations of phi of tau, but they're still present. And if we think about these directions as giving us the boundary gravitational fluctuations of the two-dimensional ADS space, then what these other directions correspond to are a bunch of massive fields propagating on that space. So these are a bunch of massive fields propagating on a fixed ADS2 space, and the spectrum of masses can be determined by looking near the saddle point here, and you find a roughly integer-spaced spectrum of masses. In particular, there's some fairly light fields of order the ADS scale. So in this model, the, quote, gravitational mode corresponding to phi is important at low temperatures, not because the other modes are all parametrically massive, like we're used to thinking about in conventional holographic setups. Instead, the gravitational mode here is important because of this small coefficient multiplying the action. Okay, but one would like to understand better the full bulk theory, including these massive modes, this infinite number of massive modes. And there is not a lot that's been understood about that. There are some, so one comment that's been made is that one should really try to understand the interactions between these modes. And understanding the interactions between them means looking at higher orders in the expansion about this saddle point, or looking at 6 fermion correlation functions, 8 fermion correlation functions. Gross and Rosenhaus have been taking the lead on this, and they find a couple of different contributions to the 3-point function, one of which looks sort of plausibly local, and the other one is non-local. I should also mention that there's an interesting proposal for a 3-dimensional interpretation that would also give a tower of these modes by Das, Yavicki, and Yoon. Okay. All right. So in the last part of the talk, the last 15 minutes or so, what we're going to do is discuss some of the interesting generalizations of the SYK model that have appeared mainly in the last few months. So there's a lot of them, and I've selected here only the ones that I find to be the most interesting. Areas of intense activity in physics research have been described by a member of the audience as resembling what happens to a cow when it falls into a river and is consumed by piranhas. I think that a more pleasant analogy would be a bed of flowers bursting forth in bloom. I mean, I think a lot of these generalizations are really interesting. So I'm going to have time to talk about the last three in a little bit of detail with a slide or two about each one. The first four, though, I'm just going to summarize with a sentence or so. So by restricting the disordered couplings in some ways, it's possible to introduce some exact global symmetry in this model, or it's possible to separate the fermions into different groups, become different flavors. One of the interesting things about what happens when you add extra global symmetry is that you end up in the infrared with additional almost zero modes. And instead of the Schwartzian action, for those guys, what you get is the quantum mechanics of a particle moving on the group manifold corresponding to the global symmetry. So in these cases, you get a somewhat more interesting infrared theory. It's also possible to do an infinite number of things involving different types of couplings, like coupling in some quadratic fermions. That tends to make the SYK model less chaotic, and there's an interesting phenomenology of what happens when you adjust the relative strengths of different terms that you can add, and the number of quadratic versus SYK fermions. Now, something that is crying out to be done to the SYK model, if you're a condensed matter theorist, is to make a lattice out of these SYK models, these strongly interacting models, and couple them together in some way to make a model of a metal. And this paper in particular was interesting. They showed that if you have quadratic interactions on the lattice between the fermions, then you get a type of flow where at very low temperatures you have something called a heavy Fermi liquid phase, and at somewhat higher intermediate temperatures they get a strange metal phase where the electrical resistivity is linear in the temperature. This is something that's difficult to accomplish by thinking about weakly coupled models. So SYK, I think, could be useful for exploring, well, it's not that I think it's useful, it's that some experts in condensed matter theory think that it could be useful for exploring some interesting metal phases. Okay, so the last three I'm going to discuss in a little bit of detail. So first, one can make a supersymmetric version of the SYK model. So instead of having a Hamiltonian that's a random sum of 4 fermion terms, you take a supercharge as a random sum of 3 fermion terms. And then you take the Hamiltonian to be the square or the anti-commutator of the supercharge. That becomes a somewhat random 4 fermion interaction with 1 fermionic symmetry. You can also do this with complex fermions, complex conjugate supercharges, and then you find then you can make a model with n equals 2 supersymmetry. So these models were analyzed in this paper, and I just want to make one interesting comment just relay one interesting comment from this paper about the zero temperature entropy in these models. So here's some histograms of the density of states in the non-supersymmetric n equals 1 and n equals 2 SYK models. And the one point is that the large N computation of this zero temperature entropy is very similar in all cases. You find a saddle point for these G and sigma-like fields, and then you evaluate the action at low temperature, and you find a non-zero answer. But the actual realization of this in the spectrum is very different in the models. In particular, in the n equals 2 case, all of the zero temperature entropy is accounted for by exactly degenerate ground states. So there's an interesting thing that happens where sometimes when the large N equations give you a non-zero zero temperature entropy, that means that there's literally exact degeneracy at the ground state. And sometimes it just means, as in these cases, that there's just a large density of energy eigenvalues relatively close to the ground state. These authors suggested this might be helpful for thinking about cases where there's a mismatch between the Bekenstein-Hawking entropy and exact counts of BPS states. One point is that although the saddle point doesn't know the difference between these, the full analysis of the low energy effective theory does know the difference. So that's the difference between the n equals 0, n equals 1, and n equals 2 super Schwartzian theories. Okay. The second generalization we'll discuss in some detail is this project of de-randomizing the SYK model. So something that's, well, the motivation for this is the following. Thinking about these disordered models is a little bit unfamiliar in holography. For example, there's no global symmetry in these models, so there's no singlet constraint that you can impose. And also there's just a puzzle, which is what is the bulk interpretation of the fact that you have lots of very slightly different quantum mechanical models with slightly different realizations of these disorder couplings. So many of us were excited when it was shown that it's possible to realize SYK-like physics in a theory without disorder. So this was building on some work by Garreau. This was pointed out by Witten. The specific version I'm going to discuss here was in a paper by Klebanov and Tarnopolsky. So the idea is that you would like to construct a clever, specific choice of fermion interactions that is simple enough to have a large global symmetry, but nevertheless gives you the SYK physics. So the one way of doing that is the following. You organize your n fermions into a 3-index tensor, where the indices of the tensor run from 1 to the cube root of the total number of fermions. And then you take a Hamiltonian, well, a 4-fermion Hamiltonian that corresponds to a particular contraction of these fermions. So we can then think about the model using Feynman diagrams. The propagator of the free propagator of the fermions looks like we have to use 3 lines, one for each of the 3 types of indices that the tensor has. And the sophisticated way to do this is to color the lines differently. The interaction vertex looks like this. It's a particular contraction of these indices. And we can use that interaction vertex a couple of times to generate this self-energy diagram. Now this is one of the diagrams that contributes to the 2-point function at large n in SYK. And in fact, one can show that the only diagrams that contribute at leading order in large n are these iterated watermelon diagrams. So for the 2-point function, you get exactly the same equations as in SYK. Now I'm not going to go through the proof of that, but, well, one comment is that the diagrams that you get are going to be slightly simpler than planar diagrams because we have these 3 index lines here. So in addition to having some planar structure, we also have to thread the 3rd index through in a reasonable way. And actually one can show that the diagrams that contribute at leading order are diagrams that are planar sort of regardless of which of the 3 colors we choose not to look at. So this 3-index tensor is a way of getting a simplified set of diagrams at large n, simpler than planar diagrams, and indeed these land on the melonic diagrams of SYK. That's at order 1 and at order 1 over n in the large n limit. Higher orders are somewhat different from SYK. Okay, but the point of this, well, one point of this is that this model now has a large global symmetry, and one could imagine gauging that and looking at the singlet sector, and it might be a little bit easier to imagine a holographic interpretation, a bulk interpretation of these models. Okay, the final generalization I'm going to discuss is ways that you can think about doing SYK-like physics in higher dimensions. So let's talk about 2 dimensions. One idea for generalizing SYK to 2 dimensions would be to continue using fermions and to take a random 4-fermion interaction in 2 dimensions. There's a difference from 1 dimension, though, which is that free fermions in 2 dimensions have dimension 1/2. So the 4-fermion interaction here is marginal, and in fact, it turns out this particular type of interaction is marginally irrelevant, which makes it somewhat complicated to get SYK-like physics. So another thing you might try is to use bosons instead of fermions. Those have dimension 0 in the free theory. So this is a relevant term, and it's going to dominate in the IR. But this interaction here is not going to be a positive potential, so this theory is not well defined. You can try to make it positive, but then there are some other instabilities that seem to make it difficult to get SYK-like physics just from a model involving bosons. Something that seems to work reasonably well is to take a model involving both bosons and fermions combined into superfields, so 1,1 superfields. And then one can write theories like this. The interaction is relevant. And, well, I'm not going to go into the details of this, but at large N, these models flow to more or less conventional, two-dimensional conformal field theories. So in particular, you preserve conformal symmetry in the infrared in higher dimensions. This funny thing that happens in one dimension where the model tries to develop conformal symmetry and sort of trips and develops instead this funny Schwartzian theory doesn't happen in higher dimensions. So, okay, well, one conclusion about these models is that they seem to be solvable CFT models with interaction strength that's of order 1 at large N. So it's not parametrically large, but it's of order 1. And so a couple of diagnostics of that, the twist of the lightest spin 4 operator is some order 1 number, and this chaos exponent lambda L that controls these commutator squareds is a order 1 fraction of the maximum allowed by the bound. Okay, so the final thing I want to mention is a puzzle that I hope that the SYK model will help us with. I guess you don't get to really demand this from the solvable models that you work with, but it would be nice if it would cooperate with us on this one. So the puzzle is the question of what corrections to a large N theory are important for telling us that the spectrum is discrete at finite N. So a concrete thing to think about is, well, we've discussed the Schwartzian partition function, which is a good approximation to the SYK partition function at very low temperatures, so large beta, which could be complex. In that limit, we get this expression for the partition function, and this goes to 0 as we make, if we take beta to be beta naught plus IT and take t to infinity. So this expression will go to 0, but in quantum mechanics, this expression here is just a sum of phases, and it should not vanish at large time. It should oscillate. So we got this expression here by processing the integral in terms of g and sigma and finding the Schwartzian theory and then analyzing the Schwartzian theory. And the question is, what is the thing that we're leaving out of the integral over g and sigma that will prevent our partition function from decaying at large time? Now, because this is a disordered model, the things I'm saying here are slightly imprecise. But in a talk later today, Schenker is, I believe, going to discuss a more precise version of this puzzle. Okay, so I have a really lame conclusion slide. So I'll just put this here. Well, okay, so we've been talking about the SYK model. Its claim to fame is that it's a solvable model that is strongly interacting. We showed that at large N and low temperatures, it reduces to this Schwartzian partition, to the Schwartzian theory, which is the same as Jakiv-Teitelbaum model in ADS2. And then we discussed a few of the many interesting generalizations that have been proposed in the literature. Okay, so thank you very much for your attention.
Yeah, thank you very much for your nice and clear talk. We have time for questions.
I have one comment and a question. You know, you use the large N saddle point method to arrive at the Schwinger-Dyson equations. And my understanding is that N must be the largest parameter of the theory for such an approximation to be valid. But then along the line, you talked about N upon beta j being small in order to, discuss the large phi fluctuations. Is there some consistency issue here about the large N method?
Right, so, well, the idea, so your first guess would be that as long as N is large, then the saddle point approximation should be good. Now it turns out that that's true for most directions about the saddle point. There's a special class of directions where that's not true. So if N is large, but N over beta j is not large, then the saddle point isn't running the show anymore. You have to do the full integral over those directions. But those directions are summarized by the Schwartzian theory, and that's a theory that's controllable at finite n over beta j, in fact even small n over beta j. So in the end of the day, you're able to analyze this theory just if n is large, no matter what beta j is.
Okay, one more, just a comment that besides this Jakiv-Teitelbaum theory that you mentioned, we have also investigated that the Polyakov model of two-dimensional quantum gravity also reproduces the Schwartzian, and all the bulk degrees of freedom are suppressed for reasons of gauge invariance. Just that comment.
Okay, yeah, thank you. Thank you for pointing that out. I should have mentioned that.
I have a question.
Are there other questions?
Yes. So in the higher dimensional version that you talked about, can you comment on the conformal symmetry at finite n?
Well, not in a very reasonable way. So I think that the most likely thing is that at finite n, there would be some kind of complicated but slow RG flow in the space of these theories with different couplings. And although, well, I don't know for sure, it's possible that there could be some large number of fixed points within that space.
Any other comment or question? I don't see any hands anymore, so we thank Douglas again.